again, continuing from where we left in the last lecture on Dart. I had ended with this explanation where we talked about the execution model of Dart. I'll begin by briefly recapping what we ended with in the last lecture. We assume for simplicity's sake that every program has only assignment statements or an if condition, which is represented as a conditional statement. Assignment statement is represented in the set A. Conditional statements are represented in the set capital C. So a program execution is a series of assignment statements and condition statements, and always ends with an abort or a halt statement. Execp can be thought of as an execution tree that consists of all program executions, which we saw an example of when we did symbolic execution. Assignment nodes will have only one successor because there is an immediate next statement, and that is only one. Conditional nodes will have a branch out based on whether the condition is true or false, and leaves will all be labeled by abort or halt. So now we will see how Dart symbolically evaluates the expression. So to symbolically evaluate the expression, Dart maintains what is called a symbolic memory. What is a symbolic memory? Symbolic memory basically tells you for every variable which is a memory address in which the variable is stored. So it maps memory addresses to expressions. For inputs, it is directly the name of the variable itself. But remember, when we did that example, for internal variables, other variables, let's say if you had z is equal to x plus y, then you need to update the value of x by using an expression for x plus y as x naught plus y naught, where x naught is the symbolic expression for x and y naught is the symbolic expression for y. So that's what we mean by a symbolic memory. Symbolic memory, denoted by S, is a map from memory addresses to expressions. When the Dart algorithm runs, it will evaluate symbolic path constraints using the algorithm and solve the path constraint to get directed test cases. Solving, it will give it to a third-party constraint solver. To start with, the inputs will all be in S. The mapping of S is completed by evaluating expressions symbolically. So for each kind of expression, I'll tell you how to symbolically evaluate the expression. Before we understand how to symbolically evaluate the expression, it's fairly straightforward. Whenever an actual variable comes in the expression, you substitute the symbolic variable instead of the actual variable in the expression. But then ultimately, if you're going to use these expressions in your path constraints to give it to a constraint solver, that's where the problem begins. I told you constraint solvers cannot handle all kinds of path constraints because the problem is undecidable. In particular, constraint solvers cannot handle path constraints that are not linear. That is, path constraints of the form 5x squared is not equal to 0. 3x cubed is greater than 0. Any kind of non-linear expression, it's not good at handling. So Dart will remember this as one of the disadvantages of symbolic testing. So whenever it encounters a non-linear path constraint, it drops it, in the sense that path constraints become non-linear. The Dart algorithm will directly use the concrete values instead of symbolic values. That's why Dart keeps the concrete values at all. So here is how symbolic evaluation of expressions happen. There is a function called evaluate symbolic, which symbolically evaluates an expression E in the context of a memory M and already available symbolic expressions capital S. So what could be various kinds of expressions? If you go back and see, the various kinds of expressions could be just a variable, a constant, an arithmetic expression, a relational expression, a logical expression, or a pointer expression. I have written only multiplication, but as I told you in the last class, it represents all arithmetic operators. This represents all relational operators. This represents all logical operators. So we'll do a case-by-case analysis of how it happens. So if it is just a variable, then you directly assign it to the symbolic expression and you return the updated memory. If it is an arithmetic expression, which is represented by the star EE prime, please read the star as standing for plus, minus, slash, mod, star, all the arithmetic operators. Then it has two operands, an expression E and another expression E prime. which first have to be evaluated symbolically themselves. So E is evaluated symbolically, E prime is evaluated symbolically, E double prime is evaluated symbolically. This is a recursive call. Evaluate symbolic calls itself. But now, if let's say this is a multiplication operator, right, in this particular case. So if both x and y are variables, let's say f and f prime involve variables, let's say f involves 5x, y f prime involves 5x and f double prime involves y, then 5xy will become a non-linear expression. And I just told you the non-linear expressions are difficult to solve by constraint solvers. So Dart has this condition. It says that if one of f and f prime is not a constant, not one of f or f prime is a constant. If one of them is not a constant, as I just told you now, you will get a non-linear expression. So if both are non-constants or one of them is not a constant, then you say now I have an expression which is not linear. So Dart keeps a special flag which it calls all linear, sets that flag to 0. If it sets that flag to 0, which means what? It's intuitively saying that Dart has encountered an expression that is non-linear. So Dart will now do concrete evaluation, which is evaluate concrete of that expression, update the memory and go ahead. Won't store the non-linear symbolic expression at all. Why will it not store? Because there's no point in storing it. Dart knows that the constraint solvers that it's going to use cannot handle these expressions. If both f and f prime are constants, then there is no expression involving variables at all. So Dart doesn't have a choice but to directly evaluate it concretely. That's what it does here. Updates the memory and goes ahead. If one of them is a constant, then what it will do is it will correctly evaluate that expression and return. Now this is the case, the rest of the operators that we saw in expressions were relational and logical operators. The only other expressions was a pointer related stuff. So this is the second case. If it's pointer, if it's the expression of the form star E prime, then it has to first symbolically evaluate E prime. So it calls itself recursively. This is a continuation of this code on this slide. If f prime is a constant, if it belongs to the domain of S, then it returns whatever value that is. Otherwise, it will return a pointer to the memory location. If it can't determine either of these, then it will set another flag, read it as all locations definite, which means it knows the locations of all the variables, in the sense that if there is a pointer that it doesn't know, then it will say there is a location that I don't know, which means it will set this flag all locations definite to 0. So, and then it will evaluate the concrete value and go ahead. So what is this part that I'm describing in? Remember, just to recap what Dart does, it takes a program, writes a driver, instruments it to first generate one random input, runs the program on that random input. As the program is running on the random input, Dart symbolically executes the program. To symbolically execute the program, it has to symbolically evaluate all the expressions. That's the part that I'm describing here. So symbolic evaluation is fairly straightforward. It will keep substituting whatever expressions that it got, normal variables with symbolic variables. That's what this recursive call does. But there's one more thing that this pseudocode establishes. It says that if, as I'm executing, if I encounter an expression that is likely to be non-linear, that is, if I'm symbolically evaluating E prime and E double prime, and one of them, after symbolically evaluating, both turn out to be not constants, then I'll say I have encountered a linear expression. So I'll set this flag, all linear to 0, go back and substitute concrete values. I will not evaluate it symbolically at all, not store it in the path constraint. Otherwise, I will do whatever normal evaluation is. Similarly here, when Dart is handling pointer arithmetic, if it encounters a situation where the memory address is not correctly known, then it will set a flag which says all locations are not definitely known, because here it doesn't evaluate all of them. So there could be places where it doesn't know. It will go ahead and substitute concrete values. Otherwise, it does normal symbolic execution. Why does it do the substitution of concrete values? Because by doing this upfront, Dart will ensure that if the path constraint that it collects is always solvable by the constraint solver that it is using. So this way it overcomes one of the disadvantages of symbolic testing. So this is the part that I was trying to explain to you. In the algorithm that symbolically evaluates expressions, there were two completeness flags that Dart kept. One flag was called all linear, which is set to 0 whenever symbolic expressions become non-linear. The next flag, all locs definite or all locations definite, is set to 0 whenever the value of a particular variable and hence the memory location of the variable is not known. When will such a situation arise? For example, you could consider a program which dereferences a pointer whose value depends on input parameters. Then I will definitely not know the value of a particular variable, right? So these situations could quite commonly arise. Now let's look at the main algorithm of Dart. How does the test driver of Dart look like? So this is the main program of Dart called the test driver or run Dart. So what does it do? First, it initializes all these boolean flags to 1. Read this as shorthand for saying all linear, which is a boolean variable, to be 1 or true. All locations definite, which is another boolean variable, is assigned to 1 or true. Forcing OK, which is another boolean variable that I'll explain now, is also assigned to 1 or true. So this is shorthand for 3 assignment statements, which assigns 3 different boolean variables, each of them to the value true. Then Dart goes into its main loop. What is the main loop? The main loop is a repeat until loop. It's a repeat until this condition is true, which means what? Both the flags, all linear and all locs definite, stay as 1. Then you keep on repeating this loop. The moment one of them becomes 0, you exit. And inside the loop, what does Dart do? Dart keeps a stack. We'll see what the stack contains. It initializes the stack to empty. I is the input vector, the vector of all inputs. It initializes it to empty. It uses one more boolean variable called directed, which it initializes to 1 or true. And then it enters a while loop. So while this directed stands for directed search. So while I am doing directed search, it has this try catch exception. So what does try catch exception do? If at some point this boolean flag forcing OK is ever set to 1, then Dart has already found an error in the program. It will print this and exit. Otherwise, Dart will go on instrumenting the program here. So it will call this method called instrument program with the stack and I. So is it clear, please, what Dart does? Dart uses 3 boolean flags, all of them set to true, and it goes into its main loop until all the path constraints that it's encountering is linear, and it knows exactly the locations of all the variables. Inside this loop, Dart will instrument the program and do a directed search. At any point in time, if Dart has found a bug, then Dart will say, I have found a bug. It will print this message and come out. So this is how the test driver looks like. It combines random testing, which is this repeat loop, with directed search, which is the inner while loop. If the instrumented program throws an exception, a bug has been found. So Dart will print that message and exit. If one of the completeness flag is being set to 0, means what? Dart has encountered a bad situation. It has encountered a nonlinear constraint. It has encountered a place where path memory of a particular variable is not known. It's encountered some bad situation. So if the directed search terminates, then the directed variable, which is this variable of this inner loop, no longer holds. Then the outer loop will also terminate, provided the completeness flag still hold. That's clear from this code, I hope. In this case, Dart terminates and safely reports that all the feasible program paths have been explored. But in case one of the completeness flags have been turned off, which is this all linear or all locations definite, the outer loop will continue forever. So there could be 3 options. Dart will explore all possible program paths successfully. Dart will find an error and stop, saying that I found an error, or Dart can run forever. That's not too surprising because it's a program analysis tools, and the problem that it's trying to handle, which is exploring all program paths, is in general an undecidable problem. So we'll now look at this code. What is the code corresponding to instrumented program in the main test driver of Dart looks like? So here is how instrumented program code looks like. It takes a stack and a vector of inputs. So first it does a random initialization of uninitialized input parameters in the memory location. So it says for each input x with I of x uninitialized, do random. This is the initial random test vector that Dart generates. It initializes memory to this value that it has found. It sets up the symbolic memory, which is S, sets the initial program, goes and says I have not yet encountered any path constraint, and begins at the first statement. And as long as it's not encountering an abort or a halt, Dart will encounter either an assignment statement or it will encounter a condition statement, because we have assumed that program execution is a series of, I'll go back to that slide for a second. We have assumed that the program execution is a series of assignments and conditions ending with an abort or a halt. So that's what this instrumented program does. So it sets up the memory, it sets its stack counter to be 0, and then it begins. So it says as long as statements are not abort or halt, it is either an assignment statement or a condition statement. So there is a switch case like. So if S is matched to an assignment statement, what will it do? It already has a symbolic memory uploaded. Here is a new assignment statement that it has encountered. For example, this could be the case that which says that z is equal to x plus y. So the memory location for z, which is m, needs to be updated with the expression x naught for x naught plus y naught. So the memory location for m is updated after evaluating symbolically the expression e with the memory location capital M and the symbolic set of expressions S. It also needs to evaluate the expression E concretely, because you don't know when in the future it will have to substitute. So it will evaluate it symbolically, it will evaluate it concretely, it will update the memory location, and it says I finished with this statement, so it will update the program counter to 1. So let's say Dart encounters a condition statement. If the match happens to be a condition, so it says if E, then go to L prime. Then what it will do is that it will evaluate E symbolically and concretely. Let's say B is the symbolic result of concrete evaluation of E. C is the result of symbolic evaluation of E. If B is true, then the then path is taken by the program. If B is false, then the else path is taken by the program. So if B is true, then it already has a path constraint which it has initialized here. It will go ahead and the condition that it got by symbolically evaluating it to the path constraint. Read this as whatever the path constraint that was earlier, now C is added to it with an AND. And then it will now put this in the stack, saying I have one more path constraint to update. I found on the way the program took a branch. Here is a path constraint. The program took a then branch. So I am putting a 1 here and adding this constraint to the stack, and it will change the statement to whichever that it has to go to L prime. But suppose the condition evaluates to false, then to the path constraint it will add negation of that condition. This is path constraint ANDed with negation of C. It will update its stack by saying the program took the else branch with a 0 and add this to the stack and change the statement number, because it's like skipping. So statement number now becomes L plus 1 and it will go ahead and do it. Is this clear? So basically this part, what it does is that it grows the path constraint one at a time. And what does the stack do? Stack keeps track of which is the path constraint that was added the latest, because that's the path constraint that Dart is going to flip to be able to get the next execution of the program. That's what Dart does here, right? It will flip it in the main thing when it does the next execution of the program. So if S is an abort or a halt, if S is an abort, then Dart raises an exception. If S is a halt, then it just directly calls the constraint solver with the path constraint that it is collected as it takes it from the stack. Now in this, it used this routine called compare and update stack. What does that do? That tells you how to update the stack. Here is the code for that. So stack has a maximum capacity. This part says as long as you've not reached the maximum capacity, if the stack branch is not equal to branch, then there's a problem. Set forcing OK to 0 and raise an exception. Where is this Boolean variable forcing OK? It was here. So if forcing OK is ever set, then you can say bug is found. Else, if stack is like this, then you go ahead and normally update the stack branch. You say you remove it from the stack, pop it off, and then add this. Is this clear? This is normally just the normal stack operations that you're doing, right? Solve path constraint, which is what it calls here, right? Solve path constraint. What does that look like? That will basically call a constraint solver, which is third party constraint solver. So what it does is that it takes the latest path constraint from latest thing from the stack, and it says if j is -1, then I finished my search, you terminate it normally. Otherwise, it says you take this whatever path constraint that you found at the top of the stack, negate that path constraint, add it to the branch, now you call it again, so that it explores the other search. This is the part that forces Dart to do the directed search. This is an explanation of what the instrumented program does. Each run of the instrumented program, the first one does a random search. So except for the first one, each run of the instrumented program, how is it executed? You have a stack of all the conditions that you've encountered in the path in the previous run. So we record a branch value and a done value. Branch value is 1, as I told you, when the then part is true or the condition is true, and branch value is 0 if the condition is false. Done value 0 only when the branch of the condition is executed in the prior runs, which means I have explored this part already. So then you say I'm fully done with this program constraint. Information associated with each conditional statement of the last execution path is stored in a variable called stack, which is what we've been looking at, and that's kept in a file that's shared between executions. And then at any point in time, whatever is available at the top of the stack is pulled, flipped, and that's the alternate path that Dart tries to take. So if it's explored both the options, then it sets the done value to 0, removes it from the stack, and takes the next available condition. Instrumented program, what does it do? It basically executes the original program interleaved with a gathering of symbolic constraints. At each conditional statement, it checks, it calls this compare and update stack routine. It checks whether the current execution path matches the one that it predicted at the end of the earlier execution. And if it is, then it doesn't repeat. But if it not, then it explores this new execution path. But if some problem happens, then it sets the flag forcing OK to 0. And basically then it will restart this run Dart, which is the main test driver, with another fresh randomly generated input. When will this forcing OK be set to 0? That can be only due to a previous incompleteness in Dart's directed search. It went along a path that it couldn't complete, so it will start all over again. So when the original program halts, new input values are generated from the solve path constraint routine that will attempt to force the next run to execute the last unexplored branch of the stack. Such a branch exists, then it's explored. Otherwise, it removes it from the stack and goes to the next path constraint that it was found. So I hope the code for Dart is clear. So the main code for Dart is this test driver, which does one random search followed by a program instrumentation which symbolically executes a program, collects the path constraint, and does a directed search. This was the code for that, which tells you how to symbolically update and execute a program. It needs a stack to be able to keep track of the path constraints. This is an update. This is the routine method that maintains the stack. This is the routine that calls the constraint solver. And Dart could, as I told you, have 3 outcomes. So here is the main theorem that talks about the correctness of Dart. If Dart at any point in time says print bug found, then there is some input to P that leads to an abort state. It has really found an error. If run Dart terminates without printing bug found, then which means Dart has explored all the execution paths of P. Otherwise, run Dart will run forever. Somebody has to manually go and abort it. The third part is an undesirable behavior of Dart, which we cannot avoid because the underlying problem is undecidable. What we'll do next time is I'll explain how Dart works for C by using an example and tell you how this interface extraction, test driver extraction, and directed search implementation actually happens through an example. So we'll stop with this for now. Thank you.